Hi, welcome to our last little bit of OS material. We got through almost all of our material last time, but I decided I could record these last 7 or so slides, and then Monday's class can be an optional class. This is where we ended up at the end of the day on Wednesday. We had talked about how the OS, as it's using a file system, it's going to cache a bunch of stuff in memory. And then it just needs to make sure it gets a chance to write out that cached information before you remove part of the file system. And the mount and unmount protocol for working with file system gives it a chance to do this. We talked about how files would get allocated. We talked about, I think, 4 different allocation methods. We need a similar method for managing free space on the disk when we need to allocate either a sector to extend a file, or we just need to make a new file. We need to find a bunch of sectors to store that file's contents, hopefully contiguous if we can. A natural way to do this might be to have a big bit vector or a section of the disk where you've got a bit for every available sector, and then you just mark them with 0 or 1s to indicate which sectors are in use and which ones are available. The nice thing about that is you can look for contiguous regions of free blocks. And then when you have to allocate those, if you can allocate them contiguously, they'll be faster to access. Even if you're not using a contiguous allocation method, still having them all in the same place on disk would give you a better chance to do that. For the FAT file system, the table that it's already using to keep up with how the blocks are linked together could also do double duty as sort of a free space array. In the table, you could use, this table here is copied from the earlier one, so maybe it's not a great example. But on the exercise, on your last exercise, you're looking at a FAT12 file system, and they use a value of 0 for a block that's free. So you could just look through that existing file allocation table, and wherever you see a 0, or even better, a bunch of zeros in a row, that's a big contiguous section of available blocks on the disk. So you don't really need a separate structure for that. For linked allocation, or even for indexed, you could use a linked list to keep up with free blocks. You could just have a pointer to the first free block, and then it could contain a pointer to the next free block, and then a pointer to the next free block. So again, even if you weren't using linked as your allocation method, you could use this to keep up with free blocks. And the nice thing is you're using the trick of using the space inside the unused blocks to keep up with the free blocks themselves. Whereas at least having a big bit vector, that's extra overhead for storing that vector. Here, you're just using parts of the blocks that are already free. Like I've done in this figure, or like your book did in this figure, it might make sense to keep the free blocks sorted on this list. That's going to be a little extra work. But then when you have to allocate space for a new file, you can look for big sections of that list that are contiguous so that you can try to keep the file all in the same place. Like we talked about with mounting and unmounting a file system, you've got to worry about the possibility that the file system data structure gets corrupted. The file system is kind of like a big data structure that's stored inside the blocks of secondary storage. And the OS is kind of always trying to keep that data structure organized so it's efficient to access, and it's trying to make sure that the data structure doesn't get messed up. But you can't always guarantee that. We talked about with removable media, I can't really keep often. I can't keep the user from just pulling removable media out before the OS has gotten a chance to write everything it needed out. Or even if it's not removable, if your system crashes partway through accessing part of the file system, then it may not get a chance to write out everything. And we'd say the file system might be left in an inconsistent state. If you think of the file system as a data structure, like any data structure, it has consistency constraints that it normally tries to maintain. Like on the file system, we might imagine, well, every block, every sector of the disk should either be part of the file, it's part of a file, it should be part of a directory, it should be on the free list. It should be in one of those places, and if it's not, we need to go find what block it needs to be part of. We could make up a bunch of other consistency constraints, like, well, no block should show up as part of two different files. No block should show up twice on the free list. If the file system ever gets corrupted, then usually we need some automatic way to go back and try to put it back in a consistent state. Even if it can't guarantee it does that perfectly, it needs to make that data structure make sense again. And this is normally done by a program called the File System Consistency Checker. Exactly what that program does would probably depend on the file system, and if your OS supports a bunch of different types of file systems, like they normally would, you'd probably need a consistency checker for each one of those. On Unix, this is normally just called FSCK, an abbreviation for File System Consistency Checker. Since your file system, especially if it's stored on a magnetic hard disk, and it's a really big data structure, running the consistency checker could take a long time. If your system crashes and then you reboot it, it used to be common to have to wait, 10 minutes, half an hour, or maybe longer to complete that file system consistency check. Traditional OSs, one reason this takes a while is the information on the file system is spread all over the disk. I mentioned this a moment ago. The OS is kind of trying to keep the file system organized, and it's trying to keep everything in a place on the disk to make it efficient to access. I don't know if you've ever run a disk defragmenter. That's what Windows and DOS systems used to do. That kind of tries to promote this. It looks at the state of the file system data structure, and it moves stuff around on the disk to try to make it more efficient to access and to try to consolidate free space on the disk. So the traditional way of thinking of your file system is it's a data structure that I have to keep organized. And I want to keep it organized, or I want to keep it distributed around the disk so that it's efficient to use. Whenever I update something, I go update it in place. So if I add to a file, I go change the last block of that file or graft on a new block or sector if I need more space for that file. So let's get everything in the right place and let's keep it there so the file system is efficient to use. And then when we have to run the consistency checker, it has to look over the entire disk, because something may have gotten broken anywhere on the disk. We'll need to check everything and make sure all of the data structures make sense. More modern file systems try to do this a little bit different. Modern file systems will often use a trick called journaling. And we've been talking in class about the ext2 file system. That has been extended to ext3, and then eventually ext4 added this feature to the ext2 file system. Like I'm trying to show in the picture, it uses an alternative approach. Back here, I was trying to say, well, traditionally, let's keep everything well organized in the file system, and then whenever we have to change something, we go change it wherever it's stored on the file system. Let's keep it in that same place. And this can make writing to the file system a little bit inefficient, because if stuff changed all over the place, you have to seek all over the place to update what's changed. And if something goes wrong, like I said, you may have to look at everything on the file system to try to fix that. A journaling file system tries to make those activities a little bit faster by having a section of the disk that is just for recent changes. And that's where the term journal comes from. It's like a log of the updated versions of any parts of the file system that changed, at least that changed recently. So if you change part of a directory, you'll have a new block for that directory, but you'll write the new version out to the journal. If you change part of an inode, you'll write the block containing that inode to the journal. So the journal is a history of really the latest version of any parts of the file system that have changed. The nice thing about putting this in the journal is when it's time to write it out, it all goes to the same place on the disk. So that's going to be more efficient. And if something goes wrong, you can look at the journal to find out recent changes rather than having to look out all over the disk. Now, if this is all you did, well, eventually your journal would fill up, and really you'd just be putting everything in the file system into the journal instead of leaving it spread around all over the disk. So the plan is we'll make sure that we eventually update the authoritative copy of each of those blocks out where it's stored in the file system. We just don't have to do that right away. We could do that whenever the disk is idle or whenever the journal gets full. So when a change happens, we first write it out to the journal, and then we update the file system when we get around to it, again, when maybe it's idle. The nice thing about this is writes can be done quickly to get them into secondary storage. We don't have to spread those writes all over the disk. And then if something bad happens, if our system crashes, the journal gives us a record of the most recent changes, even if we never got around to updating that on the file system. And this does make consistency checking a lot faster. We look at the journal, and for anything so hopefully the journal is just a tiny section compared to the rest of the disk. So we look at the recent changes. If those changes have already been written out to the disk, then we can forget about them. The file system's already been brought into a state that reflects those changes. If they haven't, well, then we can update the contents of the file system based on the copy of that block in the journal. If a change got made and it never got written out to the file system, and then it never got written out to the journal, then we're going to lose that change. But at least the rest of the file system is in a consistent state, and we don't have to hunt around all over the file system to find blocks that were written out, or at least find changes that were only partially written out to that file system. So the journal, I guess I would say it does two things. It lets us handle writes to the file system efficiently, and it gives us an efficient way of handling recent changes if the file system ever ends up in an inconsistent state. And that gets us to the end of our file system material. We spent some time at the start talking about kind of what a file system is, what we need to keep up with for each of our files, and then for the whole file system. So that usually included contents and attributes for all of our files, along with usually a tree-shaped naming directory structure, or maybe a fancier structure like a directed acyclic graph. We looked at, in class, we mostly talked about ext2 as a good contemporary example of that. And I know on your exercise, you're doing a much older, much simpler system in the form of FAT12. We talked about a lot of the jobs the OS has to do to handle this, which is mostly trying to make access to that large secondary storage device quick and easy for processes, usually by bringing stuff into memory and accessing the in-memory copy when it can, and the disk only when it has to. And this is just another example of something we talked about in our first week of classes. The OS is using that part of our memory hierarchy to cache in main memory things that would otherwise be stored in secondary storage. It's using a smaller, faster region of memory to transparently let us access the parts of a bigger, slower region of memory more efficient without our programs having to do anything extra to get that benefit. That gets us through all of the material. I'll redo this last little part of the lecture on Monday if you don't choose to watch it. But if you watch this on Monday, we'll still plan to go over material from the whole semester and to try and help you make sure you're ready for the final later that week. I'll see you on Monday. Have a good weekend.